So to start, we just want to introduce this idea of simple probability. And at its core, the idea here is that the probability of what we'll call for now event A, and event A could be anything we choose, but the probability of event A occurring is equivalent to the number of matching outcomes divided by the number of total outcomes. Now, of course, we need to be specific about what we mean by matching outcomes and total outcomes, but the idea is that matching outcomes are any outcomes that satisfy event A, and total outcomes are all of the possible equally likely outcomes that could occur in the scenario. So for instance, let's take a very simple example of flipping a coin, and we're looking for the probability that we get heads when we flip the coin. So in this very simple scenario, we flip a two-sided coin one time. On one side is heads, on the other side is tails, and we want to know the probability that we get heads when we flip that coin. So in this case, event A from our formula is the event that we get heads. So we could either say event A is heads, and we could calculate the probability of event A like this, or we could also write it this way, the probability of getting heads. We don't have to write event A specifically. We can just write the probability of getting heads. So the probability of flipping heads is equal to, well, what are the total outcomes in this scenario? We can either flip heads or we can flip tails. There's two possibilities, two equally likely outcomes from flipping this coin. So the total number of all possible outcomes in this scenario is 2, heads or tails. This idea then of matching outcomes is the number of outcomes that match our scenario here of event A, which is heads. We're interested in flipping heads, and so only one of the two scenarios matches that event. If we flip tails, it doesn't match this event of getting heads. Only getting heads when we flip the coin matches this event, so the number of matching outcomes is simply 1, which means that the probability of flipping heads when we flip a coin one time is 1/2, or 50%. 1/2 is equal to 50%. There's a 50% chance we get heads when we flip a coin. What about a different example here where we roll a 6-sided die one time and we want a 2? What's the probability that we get a 2 when we roll that die? We could write this scenario as the probability of getting a 2, so we might write it like this. The probability of rolling a 2 is going to be equal to, if we're rolling a 6-sided die one time, of course there are 6 total possible outcomes, all of which are equally likely. We could roll a 1, a 2, a 3, a 4, a 5, or a 6. There are 6 different outcomes we could get when we roll that die. So 6 equally likely outcomes, 6 total outcomes. And the number of those outcomes that match our criteria here of rolling a 2 is of course just 1, because if we roll a 1, a 3, 4, 5, or a 6, that doesn't match our criteria. Only rolling a 2 matches our criteria. So there's only one possible outcome, one matching outcome to the one that we're looking for. So the probability of rolling a 2 is 1/6. We can also do something a little more complicated where we say, what is the probability of rolling an even number if we roll that 6-sided die? Well, we might write that as the probability of rolling an even number. And we already know from this previous example that there are 6 possible outcomes when we roll that die, 1, 2, 3, 4, 5, and 6. And of those possible outcomes, only the numbers 2, 4, and 6 are even numbers. 1, 3, and 5 are odd numbers. So the only matching outcomes are the outcomes where we roll a 2, a 4, or a 6. That's 3 possibilities. So the probability in this case is 3 matching outcomes over 6 total outcomes. And then whenever we can, we always want to simplify our fraction. 3/6 is equivalent to 1/2. So we could write this as 1/2 or 50%. So there's a 50% chance, there's a 1 in 2 chance that we roll an even number. And then just one more example where we roll a die. What's the probability that we roll a number on that die that is greater than 2? So we could write this a few ways, but let's just say the probability that x is greater than 2, meaning our die roll results in a number that is greater than 2. Well, we know there are 6 possible outcomes, 1, 2, 3, 4, 5, or 6 when we roll that die. But what about the matching outcomes? Well, the numbers on the die that are greater than 2 are the numbers 3, 4, 5, and 6. The numbers 1 and 2 are not greater than 2. Only 3, 4, 5, and 6 are values greater than 2, which means there are 4 matching outcomes. And so our probability is 4 in 6 or 2 in 3, a 2/3 chance, a 2 in 3 chance, or an approximately 67% chance of rolling a number greater than 2 when we roll that 6-sided die one time and we're looking for a number greater than 2. Okay, so we understand this general idea that probability of event A, the probability of flipping heads or rolling a 2, rolling an even number, rolling a number greater than 2, it's just the likelihood that any of these events happens given the scenario that we're setting up. So just think about probability as likelihood of that event occurring. We also want to be aware at this point, though, of this idea of complementary probability or the complementary event. And the complement of any event is the scenario where that event does not occur. And we would write it like this. If we're looking for the complement of A, we might write it as P of A prime. And this would indicate the complement. So here, if we're looking for the complementary event of flipping heads, we could write it this way, heads and then prime. This means the complement of the heads event or the probability that we don't flip heads when we flip a coin one time. Well, there's 2 ways to calculate this. We could, of course, think about going back to our original probability formula and calculating it manually or from scratch. So the probability that we don't flip heads, well, if we flip a coin one time, we know there are 2 possible outcomes. That stays the same. The possible outcomes are heads or tails. The only outcome out of heads or tails that meets this event, not heads, is tails. And so there's one way that we can match this event, not heads, and that's by flipping tails. And so the probability of not heads is 1/2. And that makes sense because not heads, of course, is equal to just tails if we're thinking about a coin. And so we could really also write this as the probability of flipping tails, and that's 1/2. Or to take another example here, we're saying the probability of rolling a 2 when we roll a 6-sided die one time is 1/6. So the probability of not rolling a 2 is going to be, again, 6 total outcomes because we're rolling a die one time and we know that there are 6 possibilities there. But then not getting a 2, well, the scenarios that match that are rolling a 1, 3, 4, 5, or 6, 5 different possible matching outcomes. So this complementary event here of not 2, the probability of that complementary event is 5/6. And we could go ahead and calculate that for these other 2 examples here. But the thing that we want to notice is that in both of our examples so far, the probability of the original event and its complement, when we add them together, we always get 1 or 100%. So the probability of heads was 1/2. The probability of not heads was 1/2. So when we add those 2 things together, we get 1/2 plus 1/2, and we get 1, or we could call that 100%. In this scenario, we had the event rolling a 2, and then the complementary event not rolling a 2. If we add the probabilities of the 2 complementary events together, we get 1/6 plus 5/6 is equal to 6/6, or just 1, or 100%. And it turns out that this is always going to be the case. The sum of the probability of an event and the probability of its complement will always be a total of 1 or 100%. And that makes sense, really, because an event and its complement represents the entire universe of possibilities, right? When we roll a die, there's 6 possible outcomes. If we're talking about the probability of rolling a 2 and then not rolling a 2, that, of course, is going to represent all the possibilities. When we're flipping a coin, the probability of getting heads or not getting heads, in other words, getting anything other than heads, is going to represent the entire universe of possibilities. Over here, when we roll a die and we're looking for an even number, the probability of getting an even number and then any possibility other than an even number is, of course, going to add to 100%. It's like saying the probability of this one section of possible outcomes plus the probability of all the other possible outcomes. That, of course, is going to give us all possible outcomes, or 100% of possible outcomes, which is why we always end up with these 100% figures when we add the probability of the event and its complement, which of course leads us into this idea that probability itself is always a value between 0 and 1, where 0, a probability of 0, means that the event will not occur, or that there's a 0% chance that that event will occur, all the way up to 1, which says that the event will definitely occur, that there's a 100% chance that the event will occur. And so then we have everything in between. If we think about this as a percentage, where this is 0% all the way over to 100%, it almost makes it easier to imagine a 0% chance that an event occurs, a 100% chance that an event occurs, and then everything in between, like on the coin flip, where there's a 50% chance that we get heads, a 50% chance we get tails. That's right in the middle of this probability scale. So what this leads us to understand then is that because summing the probability of an event and its complement is always going to lead us to this 100% figure, we know that we can always find the probability of the complement as 1 minus the probability of the event itself. Or we could write that in reverse as the probability of event A is equal to 1 minus the probability of the complement. These formulas are equivalent, they're just reworked a little bit or rewritten in different ways. In other words, if we know that the probability of rolling a 2 is 1 over 6, and we want to calculate the probability of not rolling a 2, all we have to do is say the probability of not rolling a 2 has to be equal to 1 minus the probability of rolling a 2. So 1 minus the probability of rolling a 2 is 1 over 6. So we get 1 minus 1 over 6, or 5 over 6. 5 over 6 has to be the probability of not rolling a 2, which is in fact exactly what we saw here. Now that we understand this idea of the probability of an event and the probability of its complement, and the fact that those two probabilities will always sum to 100%, let's circle back to this original probability formula and talk about this idea of experimental versus expected probability. So we just talked about the idea of flipping a coin with two sides, heads and tails, and we said that the probability of flipping heads was going to be equal to a 1 in 2 chance, one matching outcome over two total outcomes, or a 50% chance of flipping heads on any one coin flip. This 50% figure that we calculated, and this formula here for the probability of any event A, is specifically what we call expected probability, or we also call it theoretical probability. It's the probability we expect to have under the given scenario. But think about this problem here. Let's say that we're flipping a coin and we flip it 5 times. So we flip the coin once and we get heads. We flip the coin a second time, we get heads. We flip the coin a third time, we get heads again. We flip the coin a fourth time, we get heads. And then we flip the coin a fifth time and it comes up tails this time. So out of our 5 flips, we got heads, 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 tails. If we look at this little experiment that we ran, what it would imply to us is that if we flip a coin 5 times, every 5 times we flip the coin, we're going to get heads 4 out of those 5 times. And so we might look at this experiment and say that there is a 4 in 5 chance, or in percentage, an 80% chance, an 80% probability that we get heads when we flip a coin. Now, of course, intuitively, we know that's not true. But if we run this experiment, it makes it look like there's an 80% chance that we get heads when we flip a coin. So what exactly is going on here? Well, we call this 80% number here, we call this experimental probability. And experimental probability can vary widely, because if we run an experiment where we continue to flip a coin over and over and over and over again, every time we flip the coin, the probability is going to change. In other words, we can see the change happen in real time, right? So if we flipped the coin 5 times and we got 4 out of 5 outcomes as heads, we would say that it looks like there's an 80% chance that we get heads when we flip the coin. Well, if on our very next flip, we flip the coin a 6th time and we get heads, there's now a 5 out of 6 chance that we get heads when we flip a coin. But if on our 6th flip we get tails, there's now a 4 out of 6 chance that we get heads as we're flipping this coin. This is an approximately 83% chance of heads, and this is an approximately 67% chance of heads, which makes sense because if our probability was sitting at 80% after we flipped a coin 5 times and got 4 of them to come up heads, if we flip heads again, then our experimental probability that we get heads is increasing. It now looks like we have an 83% chance of getting heads. If we flip tails, then that probability of getting heads is going to go down. It drops from 80% chance to 67% chance. So we can see our experimental probability moving and changing every time we redo this experiment. So every single time we flip the coin as we continue this experiment, our experimental probability of getting heads is going to move in one direction or another. So that experimental probability can vary widely, but the expected probability stays fixed. The expected probability is given by this formula here of matching outcomes divided by total outcomes, and it's the kind of probability that we're used to thinking about. What this law of large numbers tells us is that as we run our experiment more and more and more and more times, our experimental probability is going to get closer and closer and closer to our expected probability. So to illustrate that, we could sketch out a graph where we have here along the horizontal axis our number of coin flips, and here along the vertical axis, the percentage of flips where we flip heads. If we think about taking this horizontal axis out to more and more and more experiments, so here we've only flipped the coin 10 times, here we've flipped it 50 times, all the way up to this far side where we've now flipped the coin 200 times. What we see is that our data should approach this 50% expected probability because, of course, we know the probability of getting heads on any particular coin flip should be 50% as long as we have a fair coin. So we should have this line here, but if we were to sketch in some data from our coin flipping experiment, it's possible it might look something like this. When we have a very small number of flips, our percentage of heads might be far from this 50% expected probability figure. And in general, with each additional flip, so maybe this is where we are at 10 flips, at the 11th flip, we might move further from this 50% line or closer to it, and we might go farther away from the line for a while. But the concept is that eventually, as long as I flip the coin enough times, this data will revert to the mean. It'll pull closer and closer into this line. And even though it might wiggle around it, like we see the data here wiggling around this line, eventually it's going to converge to this 50% line, which is our expected probability. So this is our expected probability. And this is our experimental probability, which wiggles in both directions, up and down around expected probability until eventually it converges to be closer and closer and closer to expected probability. And experimental probability will get closer to expected probability the further we go out along this horizontal axis. In other words, the more times we flip the coin. That is the law of large numbers. It tells us that experimental probability will get closer and closer to expected probability as we run the experiment more and more. The reason we bring this up, experimental versus expected probability, is to illustrate basically 2 main points. The first point being that the fewer times we run the experiment, the more variability we can expect, and the further away we can be from expected probability without even necessarily realizing it. And so this is a good lesson for us to learn when we are running experiments and calculating probability. The idea being that the smaller the sample size we have, the fewer number of times we flip the coin, the fewer number of times we roll the die. If our data is such that we can't necessarily calculate this perfect expected probability number, we can't fill in this formula, and instead we have to experiment to see what our probability figure is looking like, then we need to realize that the chance of getting an inaccurate figure for probability is higher when we're taking smaller samples, when we're sampling a smaller number of data points, which means our conclusion then is that in order to get a more accurate estimate of probability, we want to take the largest sample that we possibly can. If we're flipping a coin, we want to flip it as many times as we possibly can to get a better estimate of actual expected probability, instead of flipping it just a small number of times and relying on whatever our experimental probability figure happens to be. So again, our two main points being that we expect highly variable experimental probability when we have small samples or small data sets. And as we increase the size of that data set, the law of large numbers tells us that we'll get closer to expected probability, and therefore our conclusion is that we always want to use the largest data set that we possibly can, or that's reasonable to use, so that we can get the clearest possible picture of expected probability.